In this bonding video, I'm going to go into a little bit of extra add-on things that I want to talk about with regard to chemical bonding and things that you may encounter possibly your freshman year of college, if not maybe a little bit after that with regard to some structures. I teach using acronyms or simple math operations to draw Lewis structures, and the acronyms that I use are ANBBLP. That's for drawing things that don't violate the octet. Again, I'm old. That's language that I was taught forever ago. Have an expanded octet is more proper there, so I have to fix that myself. And then we have a method called CHT-BPE. I use this if we have externally bonded halogens and if we have compounds that may in fact have that expanded octet. And lastly, we have a method here called CBLOP, C-B-L-O-P, and this is for oxyions and other oxygen compounds that could have an expanded octet. Now this doesn't cover everything that you would draw, but this is probably 95 to 99% of the molecules that you would have to draw in high school or your first year of college. I did a little bit of surveying. I ran into a situation with a question about a year ago or so, and started talking to my students, and I found that there are some discrepancies with regard to drawing a few molecules, some of which most freshman college textbooks do it the way that I would do it on a prior video, but I do want to go into another alternate drawing and why that actual alternate drawing probably is better, despite the fact that 60 to 70% of your freshman textbooks draw it the way that I would have drawn it in prior videos. The molecules I want to talk about here specifically are ozone, central oxygen with two externally bonded oxygens, and sulfur dioxide. We run into some key differences with regard to drawing these. And I'm going to go back through how I would have drawn these in prior videos. I would have used this ANBBLP where we do our number of valence electrons, so we would go 6 plus 6 plus 6, and we get 18 needed. We're locking this into not having an expanded octet when we use this procedure, so we're saying we want to get to 8, 8, and 8, there for a total of 24. 24 minus 18 means that 6 of these electrons have to be bonding electrons, and that gives me 3 bonds, 12 leftovers, or 6 lone pairs of electrons. So I draw my central oxygen, bond those on, I end up with this extra bond. Where does it go? It doesn't matter. It can go between either. So I'll put it there, and then I'll go ahead and finish out those lone pairs. There's 1 pair, 2 pairs, 3 pairs, 4, 5, and 6. And we know that this has another major resonance contributor where that double bond is to the other oxygen. And we get a structure that looks like that. And the geometry there, although I don't really reflect it in the drawing, is that it's a trigonal planar domain, an angular molecule with a slightly less than 120 degree bond angle. And for ozone, that is completely correct. If I do the exact same process, I'll get a very, very similar structure with regard to SO2. Because sulfur and oxygen as a central atom are in the same family on the periodic table, so we're going to have 6 as that number of valence electrons on the central atom. The problem that I've encountered is with regard here to the SO2, and one of the things that you have to think about once you start getting further down the periodic table is you do run into D sublevel existence there, which can alter structures a little bit. Now I read an article from the ACS, and they're not so sure even that that's what's going on with regard to sulfur dioxide. There's a little bit of a discrepancy there with it, but it seems as though this structure right here probably, based on scientific evidence, really doesn't describe the structure of SO2. So then how could we draw it some other way, and why might this be wrong? Well, one of the issues with this, if you count contributing electrons from each atom, this oxygen over here has 1, 2, 3, 4, 5, 6, that's normal. Sulfur, 1, 2, 3 from the bonds, 4, 5. So sulfur here has essentially lost an electron, so it's going to have a formal charge when we draw it that way. And the oxygen here on the other side, 1, 2, 3, 4, 5, 6, and 7. So that's kind of an issue because now we've got these formal charges. And again, this also would have major resonance contributor if that's the structure. That would look like that also. But in order to minimize formal charges, when we have this, we need to re-examine, is there something else that can be going on, and is there some other way to justify another structure for sulfur dioxide? Now, again, I surveyed my students, and probably close to 60% in college said this is the way that their textbook does it, this is the way their professors are doing it. For the most part, I found in the AP community, this is kind of what we're seeing, although I did go back on an old test, and I found a little bit of a weird question with regard to sulfur dioxide that kind of supports a little more modern evidence with regard to its structure. So how else could we draw SO2 and potentially come up with a different structure? Now, an organic chemist, they would look at this structure and they would say, you're still going to get the same bond angle, you're still going to get the same domain, the same geometry. Organic chemists, I talked to them about it, and they're like, it doesn't matter. It's the same whether we put that double bond in two locations, whether we talk about it, from a delocalized standpoint. Again, this does not change things with ozone. Everything I'm finding with ozone, delocalized pi bond, with a decimal bond order. However, with sulfur dioxide, most evidence seems to support, modern evidence seems to support that that's not what's going on. So we're going to have to draw it with this expanded octet option with regard to the central sulfur and these externally bonded oxygens. And I kind of like this, especially from a standpoint of what we know about sulfur as a compound itself. It actually supports a little bit more of the quantum mechanical structures of sulfur by doing it this way. Again, your molecular orbital approach tends to produce this drawing that we have here, and that's what we see, with regard to most first-year chemistry books. But again, if we're trying to minimize the formal charge, then we're looking here. Is there some alternate drawing? All right. So how can we do this? Well, I'm going to use this C-block method, where C stands for central number of valence electrons around the central atom. That's my sulfur. That is 6. Bonds, calculated charge on the central atom, treat oxygen as a -2 since it's the more electronegative, and then calculate the positive charge on the central atom. So that means that there will be 4 on this central atom. And again, that's very, very supported by the fact that, sulfur is an S2P4, 6 valence electrons. So if we talk about sublevel shielding, it actually supports this drawing, as we see with most of these drawings from this particular acronym. Lone pairs on the central is central minus bonds divided by 2. So that is 6 minus 4, which is 2, divided by 2 equals 1 lone pair on the central atom. The next thing is oxygen electrons, 6 times the number of oxygens plus any type of formal charge, which we don't have a formal charge here, so that would be 12. And then lastly, pairs on the oxygens is the oxygen electrons minus the bonds, pairs on oxygen. Try that again. Oxygen minus the bonds, so 12 minus 4, all right, which is equal to 8. And then because it's bonds, that's 8 bonding electrons. That's where I sidetracked there a second ago. Used to doing that a little bit different. And then divide that by 2 to get the actual number of bonds. So we're going to have 4 bonds here on this. So what we end up with is a structure that looks like this, which again, from a standpoint of an organic chemist, they're going to look at that and say, it's really the same as a blended resonance, other than the fact that this is not a delocalized pi bond. This is actually 2 double bonds that we have in this structure. And it definitely supports the fact, that we talk about sulfur, with a 4 charge when it's with something more electronegative because of those p sublevel electrons. More recent research from 2015, there was a thing in the Journal of Physical Chemistry, and they actually talk a little bit about sulfur dioxide and how it actually has these two double bonds, as opposed to a delocalized pi bond. Now they actually mention in there that it's not because of the 3D orbitals, which that was the part that was, a little bit confusing to me, because I know, once we start to get down into here, we start mentioning, well, we're in the third energy level, and we know that we have 3D electrons, and that sometimes can change things structurally. But they actually talk about the fact that that's not what it is. And again, I'm gearing this lecture more toward first year chemistry, so I'm not going to go through that entire article that we find with regard to that. So again, this is what we get when we draw this with an expanded octet. If we draw it without the expanded octet, we end up with this structure, again, which has another major resonance contributor, the double bond as a delocalized pi bond in another location. But this second drawing does have formal charges. So, here we have an issue where we're dealing with formal charges. Here we have an expanded octet. Again, more modern research seems to indicate that the expanded octet is probably the more likely explanation for sulfur dioxide, even though, with that said, most chemistry, freshman chemistry textbooks and even high school chemistry textbooks tend to address this molecule in another fashion. So I want to go through and I want to do this video just in case you encounter that situation where you're trying to draw that, and my answer is you got to do what you do to get through. If we're doing this through molecular orbital, and this is what your book has and this is what your professor has, then that's definitely the way to do it. If not, you just use that other acronym. Do you use, again, my acronyms, if you're using those, do you use ANBBLP as a simple math operation, or do you use CBLOP, where you end up with that expanded octet? I did a little research and I came across this question, and when I first saw this question I thought, oh, okay, so here we go. The AP community tends to talk about this like we have right here in this drawing, and this question actually, to me, was a little bit misleading. I think students, my students, I think would miss this particular question. Of course, it is an older AP exam question, but it shows these two major resonance structures and it talks about them having the same length. So immediately I'm looking at this saying, well, this is two major resonance contributors. It's going to have that delocalized pi bond. But if you take a look at the scoring rubric, and again, this is an older question. I haven't looked on the discussion board to see if this has actually been addressed or not. Here, when we go through this, they talk about your drawing, but they actually say, that you get a point for stating that both bonds are double bonds. So if you were to go through this and talk about delocalized pi bonding, rather than stating that both are double, it looks as if you would not get credit. So that seems to be, a little more consistent with using an expanded octet for the drawing of sulfur dioxide. Again, even though that does tend to differ a little bit from what we see in most AP chemistry books and most freshman college books, throwing this out there, with me and my students, I'll address it one particular way within the classroom. But if you're watching this video and you're in freshman college, whichever way it is you're doing it, you're taught to do it, you still got the acronyms there. You just need to know which way to handle that particular molecule. Thank goodness that's one of about, 500 molecules that you may potentially draw or work with. So, it's not too bad. You just make a little side note of, oh, well, that has two. And hopefully that'll carry you through tests, quizzes, whatever it is you got to do to pass the class.